Okay, so here's a problem that ends up comparing arithmetic and geometric sequences. Your current salary is $60,000. Find which of the following two options would yield more total income over the next 10 years. So option one is a $3,000 raise every year. So you start with 60, then 63, 66, 69, etc. Option two is a 4% raise every year. So it's interesting to actually look at that first raise, 4% of $60,000. If you want to calculate it, it's $2,400. So you don't get as much of a raise the first year. But that 4% might add up because as your salary goes up, that raise is going to go up as well. So it's not clear exactly which one is going to win out. I set it up to be pretty hard to guess. Okay. So option one is an arithmetic sequence. That's the key. A sub 1 is 60,000. The raise was given as 3,000. N is 10. That's the next 10 years. Okay. So the final salary is 60,000 plus 9 raises, that's crucial, of $3,000, 27,000 plus 60,000, $87,000. Okay. The total income, very much like the problems we've been doing so far, is on average, you're making the average of $60,000, $87,000 a year. One way I was talking about it with a student was if all you told me, if you didn't tell me anything else about exactly the raise structure or whatever, it's a simple pattern or whatever, if you told me 10 years ago I made $60,000 and this year I made $87,000, and I wanted to get a guess of like on average how much has he been making in the last 10 years, I would do this, but I would think of it as an approximation. The cool thing about an arithmetic sequence, and pretty much only an arithmetic sequence among the ones we deal with, is that's actually the right answer for the average salary. He's been making this much money. What is that? $73,500 on average for a year. Oh yeah, I could have gotten that by dividing by this by 10. And then so over 10 years, he's going to make $735,000 total. Okay, so I really like thinking about this as take the cheesy average, which sometimes is correct for arithmetic anyway, and then just multiply by 10. Okay, so $735,000, not so bad. Okay, option two, the key is that a percentage raise is a multiplier. And this is very much like compound interest. We've been doing it for the last couple months, over and over again in different ways. A sub 1 is 60,000. Now the ratio is not 0.04. That would suck. That'd be the next time you'd only make the $2,400. The ratio is our usual 1 plus the percentage increase, 1 plus the interest rate kind of thing. So the ratio is 1.04. You multiply that by $60,000, you're going to get the 60,000 plus the 2,400. 62,400 if you want to do it, work it out yourself. Okay. Again, n equals 10. Okay, this is exactly what we need for our formula. Okay, now the final salary, I kind of want to look at what you're making in that last year. You don't really absolutely need it, but let's go ahead. Give yourself 9 raises from year 1 to year 10 of 4%. This is exactly the compound interest formula. This is what you'd get if you put $60,000 in the bank as well at 4% interest, compounded yearly for 9 years. Okay, but here's the final salary, about 85,400, just shy of 85,400. Okay, so not as much as the final salary here, so strongly suggesting that we're not going to measure up on the total either. Okay, but we might as well get that total. It's not that hard. 60,000 times our wonderful formula, shortcut formula for the sum of a geometric sequence. You plug that into the calculator, might as well. I wouldn't want to do that in my head. 720,000 and a little bit more. Okay, so it actually is better here to keep taking those arithmetic raises because the 3,000, 3,000, 3,000 is better than the 2,400 and then a little bit more than 2,400 and a little bit more. Okay, so option one is superior. Most of the time, though, I should note, realistically, employers usually calculate they're more likely to have like a percentage-based raise, although both options or more complicated versions are definitely on the table. Okay. Now let's look at this. The $85,000, the next 4% raise you're going to get though is $3,400. So you're going to start making up after this 10th year. You're going to start making up more money. You're going to get bigger raises than the other guy. So after 20 years, I would guess, I didn't calculate it out, but I'm pretty sure after 20 years, option 2 is going to be better. And it's an interesting question to kind of play with the numbers here. And if you want to figure out which one wins, or when does the percentage-based raise beat the flat fee raise, the $3,000 a year. Okay. Okay, so here's a rather bit of a different one. I think I'll just do this one and then quit for today. Consider the sequence defined recursively by a1 equals 3, and a sub n is a fairly complicated gadget. It's a case statement. It's like a piecewise thing. And it says triple your previous value and add 1 if your previous one is odd. Have it divide by 2 if the previous one is even. Okay. That's very interesting. And this is not geometric. This is not arithmetic. This is back to, can we understand in a somewhat complicated situation what this idea of recursive definition means? Okay. So here, when I asked this on a test before, they had various misinterpretations, but one of them was just really not thinking recursively. And in particular, not being careful about what this was. A really big mistake is not to keep clear the difference between n, the label for the term, just which term is it in the sequence, 1, 2, 3, 4, 5, 6, and a sub n, or a sub n minus 1, or whatever, which is the actual value of the interesting numbers you're generating. So all the a sub n's are the interesting numbers you're generating. So this says if you look at the previous number in the sequence, not where you are in the sequence, and if that's odd, you triple and add 1. Here, if that previous number is even, you have it. And that makes sense. You wouldn't want to do this. Well, it turns out the part of the point here is we want a sequence that's all integers. Unlike things like 1.04 in that previous problem, for example. This makes sense because if a sub n minus 1 is even, you can have it and still be an integer. Okay. So let's look at it explicitly. You start out with 3 by definition. Because that's odd, it's not because the 1 is odd. We totally don't care about this number, as we often do with recursive definitions. It really doesn't come in. 3 is odd, so we triple and add 1 and get 10. Okay, so it's because this number was odd, not this guy. Okay, now that one is even, so the rule is if that's even, you have it. So the next thing is 5. Okay, now you triple that and add 1 and you get 16. Okay, that is even, so the next one is 8. Now that's even, so the next one is 4. That's still even, the next one is 2. That's still even, the next one is 1. And then and only then do you go to triple and add 1 again. That gets you to 4. Now that's interesting. We've seen that number before. And because this sequence only cares about what the value is, you're going to repeat the same thing. You're going to have it and get 2. And then have it again and get 1. And then what's going to happen? The next one is going to be 4 again, because now it's an odd number. You triple and add 1. Okay. So the cool thing about this is that even though it's a complicated rule, we can absolutely confidently predict what a of 750,000 is going to be, or any a, because we see this repetition. As soon as you get into a 4, 4, 2, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1, whoops, sorry. That's, hello. They're going to repeat. Okay, and that's what part B was, describe the behavior of the entire sequence. So, at least in this case, with this funky rule with triple and add 1 or divide by 2, if you start with 3, you don't immediately start cycling, but eventually you get trapped in this cycle 1, 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4. Okay, so an interesting question is if we'd started with a different seed number with the same funky rule, the same rule of triple and add 1 for odd numbers and half if you even, what would happen? It's a really fun thing to experiment with. Sometimes the numbers get rather large, but it turns out that no matter what you put in, unless you discover something very unexpected, eventually it gets trapped in the cycle 1, 2, 4, 1, 2, 4, 1, 2, 4. Okay, but it's a famous unsolved problem to prove that no matter what positive integer you start with, it eventually ends up in that cycle. Okay, it would be a big deal for somebody to prove that. It's not like people don't think of it as a founding piece of mathematics, or that it opens up a lot of doors to other pieces of mathematics, but it's a very famous and simply posed problem, and nobody has proved that it always does this repetition.